The universal gas laws, the law of gravitational attraction, as well as many other laws of nature can be modeled using power functions. Hi, my name is Tom Atwater, and today we will be investigating power and root functions. Let's start by discussing the formulas for power and root functions. A function f given by f of x equals x to the b, where b is a constant, is a power function. If b is equal to 1 over n for some integer n greater than or equal to 2, then f is a root function given by f of x equals x raised to the 1 over n, or equivalently, f of x is equal to the nth root of x. Let's look at some examples of power functions. We have y equals the square root of x, and we would notice that that starts at 0, 0, and it has a domain of 0 to infinity and a range of 0 to infinity. For y equals the cube root of x, this is the graph of that function, and this time notice that both the domain and range are negative infinity to positive infinity. And here we have y equals x raised to the 2/3 power, or the cube root of x raised to the power of 2. And here is its graph, and you will notice that the domain goes from negative infinity to infinity, but the range this time is restricted to 0 up to infinity. Now, let's summarize our findings about the domain of power functions. If the rational number p over q is written in lowest terms, then the domain of f of x equals x raised to the p divided by q is all real numbers if q is odd, and is all non-negative real numbers if q is even. If b is irrational, then the domain of f of x is equal to x raised to the b is all non-negative real numbers. Well, let's jump right into an example. Let's look at the table that lists the weight W and the wingspan L for birds of a particular species. And there we see our table with the weights of 0.5, 1.5, 2.0, 2.5, and 3.0, and the wingspan L as being 0.77, 1.10, 1.22, 1.31, and 1.40. Use power regression to model the data with the formula L is equal to A times W raised to the B. Graph the data and the equation. Approximate the wingspan for a bird weighing 3.2 kilograms. And here's the graphing calculator emulator software, which works for both the TI-84 Plus as well as the TI-83 Plus. I'm going to enlarge the screen, which is the output screen of your calculator, and over here are the keystrokes that I'm going to be following to do this power regression. All right, the first thing we need to do is get it into statistics mode, and so that you click on the stat key, hit the enter key to go into the place where we can enter the data. So the first set of data is going to be for the W weight, so it's 0.5, then 1.5 and click enter, then 2 and click enter, then 2.5 and click enter, then enter 3 and click enter, then use the move to the right arrow so that you can go under line 2, and now we'll enter 0.77 and click enter, then 1.1 and click enter, then 1.22 and click enter, 1.31, click enter, 1.4 and click enter. Then what we need to do is click on the Stat button again, and we need to go over to Calc for Calculate, so click the right arrow over 1. But now we need to move all the way down to Power Regression, and you'll notice that we don't even see it yet, so we're going to have to move down 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and 11 spaces to get down to Power Regression. Now we click on the Enter key, and it says, okay, you want to do a power regression? And the answer is yes, we do. So click on the Enter key again, and it's working through, and here it comes up and gives us that y is equal to a times x raised to the b. And it gives us our a as 0.9674, and I will round it off to that. And b is equal to 0.3326, because I'm rounding that off. All right, the next thing is, in order to graph this equation, we have to set up the window so that we have a minimum of 0 for x and a maximum of 4 for x. We'll leave the scale at 1. But now, for y, the minimum, we're going to use negative 0.5. And for the maximum, we're going to use 1.5. Now we need to click on the y equals key so that we can enter that equation that the calculator just did in the power regression. So that's y1 is going to equal 0.9674 times x raised to the power 0.3326. And now we can graph that. And you will see that it has the shape of a root function because the exponent was 0.3326. This next part of the keystrokes is to find the actual value for the kilogram weight of 3.2. So what we do is hit the second, then the trace button, then we click on x equals 13.12, so we get 3.2, and when we click on enter, it shows us clearly up here is the 3.2, and we see that the wingspan down here is 1.42, and I'm going to round that off, 1.42 meters. Now, in this particular case, the graphing calculator made it tremendously much easier to do that power regression. Let's investigate the power function in more detail. So we have the root function when n is even, so f of x is equal to the nth root of x. And on the right-hand side over here, you'll notice we have the examples y equals the square root of x, y equals the 4th root of x, the 6th root of x, and the 8th root of x. What you'll notice from those 4 graphs, which are all very similar, is that as the power of n gets larger, the graph lies closer and closer to the x-axis. In addition, the domain is from 0 to infinity, inclusive of 0, and the range is inclusive of 0, also to infinity. We say that this graph increases on its entire domain, and we also say that it's continuous on its domain of 0 to infinity. Let's look at the power function when n is odd. So we have the root function, n is odd, so f of x is equal to the nth root of x, but n will be odd this time. So we have examples of y equals the cube root of x, the 5th root of x, the 7th root of x, and the 9th root of x. The first thing that I want you to notice is that in both cases, the domain and range are now negative infinity to infinity. Once again, as the root number increases, the graph gets closer to the x-axis. We say it once again that for n being odd, the function increases on its entire domain, negative infinity to infinity. It is also continuous on its domain of negative infinity to infinity. And so let's do an example where we find the domain of f of x is equal to 4x plus 12, and we find the domain, the cube root of negative 8x plus 8. So we take the first function, and the first thing we should notice is that f of x is equal to the square root. That's an even function. And that tells us that we need to make sure that underneath the radical, it is a positive number. So we have 4x plus 12 greater than or equal to 0. So, of course, 4x is greater than or equal to negative 12. X is greater than or equal to negative 3. So the domain is negative 3 inclusive up to infinity. For part B, we have f of x equals the cube root of negative 8x plus 8. But we don't really have to do anything here other than remember that when you have an odd root, in this case the cube root, that your domain is always negative infinity to infinity. All right, let's review transforming graphs by doing an example. So let's look at the following example that involves transformations. Explain how the graph of y equals the cube root of the quantity negative 8x plus 8 can be obtained from the graph of y equals the cube root of x. Then graph both equations. So I would start off with y equaling the cube root of negative 8x plus 8 and do a little bit of work to that. So let me write that down. Y equals the cube root of negative 8x plus 8. The first thing that I'm going to do is notice that they have a common factor of 8, and also be a little bit sneaky and say, well, really, I can pull out a common factor of negative 8 and say that I have the cube root of negative 8 times the cube root. Now watch what I do with this. This would be positive x minus 1. Okay, but now the cube root of negative 8, we actually can simplify. It's equal to negative 2. And then we have the cube root of x minus 1. So when we look at this, what we're going to notice is this gives us a shift right of 1 unit. The negative and the 2, that vertically stretches it, and the negative reflects that over the or across the x-axis. So just graphing these by hand, what I have is the original of y equals the cube root of x. I'm going to have the graph going like this. But now, when I want to do my shift right of 1 unit, that would shift it this way, 1 unit, so that point comes here. But it also gets vertically stretched like this, so it's going to be bigger this way, but then it needs to get reflected across the x-axis. So I'm going to draw two things. The vertical stretch would be something like that. And then I have to reflect it over the x-axis. So what is going to happen is I need to take this and flip it over to here. And take this and flip it here. So this is my graph, the more solid line for y equals negative 2 cube root of x minus 1. Well, next, let's look at graphing circles using the root functions. The equation of a circle with a center at 0, 0 is x squared plus y squared is equal to r squared. However, that's not a function. To be able to use the graphing calculator, we must solve for y and then graph the two root functions, each of which is a semicircle. We have y equals the square root of r squared minus x squared, which is the semicircle that would be above the x-axis. And then we have y equals negative the square root of quantity r squared minus x squared, which is going to be the semicircle below the x-axis. So let's actually do an example of a circle. Use the calculator in function mode to graph x squared plus y squared equals 4. Use a square window and a decimal window. Okay, so here's the graphing calculator. The first thing I want to do is click on Window and set it up to be a square window with -4 as the minimum for x, and actually -4.7, sorry, for the minimum for x. For the maximum for x, we're going to use 4.7. We're going to leave the scale as 1. The minimum for y, we're going to plug in as -3.1. And then for the max y, we're going to plug in +3.1. And this gives us a square window using decimals, which will allow us to draw a smooth circle once both root functions are graphed. Now let's click the y equals key, in other words, the equation key, and enter those two equations. We're going to have the square root of the quantity 4 minus x squared, and close parentheses, then move down to the second line. And what I'm going to do here is, instead of rewriting that whole thing as the negative square root, I'm going to put in the negative, but then I'm going to hit the variables button. I'm going to tell it that we want to use the y variable, so I'm going to have to move over to the right for y variables. Function is what we want, so I'm going to click enter. And y1, which was the first equation I entered, is the function we want. So we're going to graph y1 as the square root of 4 minus x squared, and then graph the negative of that. So let's hit on the graph key, and you'll see in a moment there's the positive, and then in another moment there's our negative. So that's how we can graph a circle using the graphing calculator. Well, now what I'd like to do is look at graphing a horizontal parabola. And a horizontal parabola, of course, means that it's going to be opening either to the right or to the left, depending on the actual equation that we're going to be looking at. So let's look at this example, or let's look at how to do it first. Graphing a horizontal parabola using root functions. The equation of a horizontal parabola is x is equal to ay squared plus by plus c, where a doesn't equal 0. However, this is not a function. And to be able to use the graphing calculator, we must solve for y and then graph the two root functions. As we did with the circle, it's going to be two half parabolas combined together to give us a parabola. Let's work out an example of this. So let's take the example that the graph is x equals 2y squared plus 6y plus 5. And it gives us the window that it wants us to use in order to have the right proportions. So what the first thing we need to do is solve that equation of x equals 2y squared plus 6y plus 5 and solve it for y. The way that we're going to have to do that is by completing the square. So let's start by writing that equation down. X is equal to 2y squared plus 6y plus 5. Okay, we need to complete the square on y squared. To do that, the first thing we need to do is divide or get this coefficient out of the way. So we're going to divide both sides by 2. That's going to give me x over 2 equals y squared plus 3y plus 5 halves. Now we want to complete the square. the easiest thing would be to move this 5/2 to the other side so that it's not part of the completing of the square on the y. So I'm going to have x over 2 minus 5/2. I'm going to leave some space here, which will be clear in a moment why. And I'm going to have y squared plus 3y. And to complete the square, we need to take the coefficient of y, divide it by 2, and then square it. So in other words, 3 over 2 squared. And 3 over 2 squared would be 3 squared 9, 2 squared 4. So that over here I left space because if I'm going to add 9/4 to this side, I must also add 9/4 to this side. Okay, so now over here, this is negative 10/4. So I get x over 2 minus 1/4 is equal to y plus 3/2 squared. Now what I do is I take the square root of both sides. So I have the square root, and it's plus or minus, the square root of x over 2 minus 1 over 4 equals y plus 3/2. And of course, the squared is canceled out by the square root. So I have y is equal to, I have to, of course, subtract the negative 3/2 from that side, and then it's going to be plus or minus the square root of x over 2 minus 1/4. So what I can do now is take this root function, or I should say these two root functions, because of course we need to break it up into the positive and the negative when we go to the graphing calculator so that we can graph those two half parabolas. So let's do that now and look at the graphing calculator, and I will call up my other script, which I wrote for this one. And let me clear this screen, and I need to just hit the clear button, and we bring it back. So now, the first thing I need to do, remember, it told us to set up a window in which the minimum for x is -2, the maximum for x is 8, we leave the scale alone, and then the y minimum is supposed to be -4, and the y maximum is supposed to be 2. Then we can go through and enter our equations. So we have negative, and one of the things is I did turn them into decimals. So 3/2, of course, is 1.5. Then plus, and I hit the second key, the squared key, which gives me my square root. I turned these into decimals as well. So 0.5x minus 0.25. Close the parentheses to show that that's the quantity underneath the square root. Let me move down to y2, and just for the purposes, we need to put in -1.5 and then minus the square root. So second square root 0.5x minus 0.25, close the parentheses, and now let's graph that. So you'll see there's 1/2 of the parabola, and there's the other half of the parabola. And you can see that the graphing calculator can be useful as long as we've changed the equations into functions, which is what we had to do with both the circle and the parabola. Well, now it's time for you to try a problem. So let's take a look at an example that I want you to do. Find the domain of the function f of x is equal to 5 plus 4x. Pause the video while you work on this problem, and when you are finished, restart the video to check your solution. All right, welcome back. Let's see how you did on that particular problem. I gave you the function f of x is equal to the square root of 5 plus 4x. And you were asked to find the domain of that. Remember, this is an even function. It's square root. Therefore, underneath here has to be non-negative. And therefore, you set it up as 5 plus 4x greater than or equal to 0. And that means 4x is greater than or equal to negative 5. And that means x is greater than or equal to negative 5/4. So the domain is inclusive negative 5/4, comma, infinity, with the parenthesis and infinity. If that's the answer you got, then you got that particular problem correct. All right, in this lesson, we explored power and root functions. Be sure to work the exercises that your teacher assigns, and we'll see you next time.